Okay, good afternoon, everybody. First of all, I would like to thank the organizers for their kind invitation and for this opportunity. I will speak about some results obtained mainly in collaboration with Giuseppe Mastroianni, and it's worth to mention. And I will focus, I will not speak about all these things, actually. I will focus mainly in best approximation and interpolation, especially in Lagrange interpolation. And this talk is dedicated to the memory of Peter Verteci, who made an important contribution in this topic. So what is our aim? Our aim is to approximate functions with exponential behavior, with some exponential singularities. In particular, we focus on the case of function defined on the bounded interval, on the open interval -1, 1, for instance, which can grow exponentially at plus and -1. And of course, we have to introduce, if we want to approximate this kind of function by means of polynomials, we have to introduce some weighted polynomial approximation process. And we will consider some Pollaczek type weights. I will define them in a minute. I will talk about mainly Lagrange, Hermite, and Hermite-Fourier interpolation. There is a vast literature on the topic. I will not mention everybody. I just want to mention the Hungarian school, and starting from Erdős and Turan, Freud, Nevai, Szabados, and also, of course, Peter Verteci. The problem is that these authors have considered mainly process based on the zeros of Jacobi weights. So these are not suitable in our case. We have to introduce different kind of interpolation processes in order to approximate this kind of functions. So weighted polynomial approximation, we have a function f, which does not belong to usual LP spaces. But if we choose a proper weight u, the product of f times u belongs to LP, and we can approximate this product by a sequence of polynomial multiplied by the weight u. Of course, the weight u depends on the singularity of the function. And we have to introduce some new function classes to characterize them, to study the best approximation, and to construct concrete approximation processes for these kind of functions. And this will be the main goal in my talk. Then, if I will have some few minutes, I want to show you how this is related with different topics in numerical analysis. For instance, the computation of integral containing fast decaying functions, or the construction of numerical methods, stable and convergent numerical methods for integral equations. So this is the outline of my talk. I will start with a few words about the weight and the orthonormal system related with the weight. What I call Pollaczek type weight is a weight of this form, decaying exponentially at the endpoints, plus and -1, depending on parameters, for instance, alpha and beta here. The behavior of this weight is essentially determined by the exponential part of the weight. You can see this algebraic factor as a logarithmic perturbation of the weight. But it's useful to have this perturbation in order to get more degree of freedom in the choice of the spaces. We will see it later. I want to point out, yes.
Potential weight goes to zero.
Goes to zero, yes, yes. So alpha is positive, and beta is non-negative. Anyway, it goes to zero very fast. Of course, when alpha increases, it goes to zero faster, of course. This is a strongly neoclassical weight. This is not a doubling weight, for instance. This weight does not belong to the Zego class for alpha greater than or equal to 1/2. But this weight belongs to a wide class of exponential weights defined and studied by Levin and Lubisky, who studied the orthogonal polynomial associated with the general exponential weights, including this kind of weights. Let me denote by PMW the orthonormal polynomial of degree M associated with the weight W, with the orthonormal polynomial with positive leading coefficient. The zeros are x1, x2, xm, belongs to the so-called Mascar-Saff interval, minus AM, AM. And the Mascar-Rachmaninoff number related to this weight behaves in this way. So it tends to 1 as m goes to infinity with an order which depends on alpha. Notice that in the case alpha equals 0, so this is the limit case when we have Jacobi weights. Here we have again 1 over m squared, as well known for Jacobi weights. Otherwise, we have an interval which is much smaller. So the zeros are closer to 0 as alpha is bigger. For this polynomial, the three terms recurrence relation, the coefficient of the three terms recurrence relation are not explicitly known. So we have to discuss, if we have time, I will say some few words to discuss how to compute these zeros. Okay, this is a similar weight function. I need two weight function essentially because in order to study my approximation process, because I choose one weight W for the orthonormal system and will be the weight related to the nodes that I will use in interpolation, and another weight U for the spaces, the function spaces I will consider. You see the weight U is very similar to the previous one. We have the same exponential part and another parameter, gamma. The weighted function space associated with U are the following. For p less than infinity, we say that f belongs to LUP if and only if f times u belongs to LP, the usual LP space. For p equal infinity, we have the space of all continuous function on the open interval with these two limit conditions, which are necessary for Weierstrass theorem. And of course, these function spaces include are much larger than the function spaces related with the Jacobi weights. Of course, much larger than classical function space, but also much larger than function spaces related with the Jacobi weights, and include functions growing exponentially at the endpoints. We can define also some subspace of LUP, for instance, the Sobolev space. I only want to point out that in the semi-norm here, we have the function phi, which is the usual phi function in -1, 1, so square root 1 minus x squared. And we can introduce, we can define some moduli of smoothness. These function spaces are characterized by this moduli of smoothness. I don't want to go into the details here, but I just want to mention that these definitions are, this is the main part of the modulus of smoothness in an interval depending on alpha. And here we have the complete modulus of smoothness. Formally, this definition is quite similar to the disymptotic modulus of smoothness. But we have a main difference, which is here, because we have a different interval where to calculate the main part of the modulus of smoothness. So the other things are more or less similar in a way. And with this moduli of smoothness, we can also define the Zygmund spaces. And in the Zygmund spaces, the two moduli are equivalent. This is useful because usually it's much simpler to compute the main part of the modulus of smoothness. But if we define the error of best approximation, so I denote by EMF UP the error of best approximation by means of a function f belonging to LUP by means of polynomials, then we proved some Jackson and Sechkin inequality with this moduli of smoothness. So this is a classical form of the Jackson inequality. And also in a weak form, which is sometimes useful because it includes the main part of the modulus of smoothness. And here you can see we have also the, in some sense, converse inequality. Not really converse, but in a way, the backward inequality. The main difficulty here is that, first of all, we cannot use the Jackson kernel in order to obtain these inequalities. So we had to construct some one-sided approximation process in order to get this. Also, another key tool is the construction of key functionals equivalent to this moduli of smoothness. And concerning this inequality, the Sechkin inequality is based, as usual, is based on Bernstein inequality. So the Bernstein inequality, in this case, assume classical form. As for formal is the same as for Jacobi weights. The only difference is that we have a different weight function here. The function phi, again, is the same function phi, as is well known for Jacobi weight. And to be more explicit, we have these error estimates. For instance, if a function belongs to the subvolume space of index R, which means that the function has R derivatives, then the error of best approximation goes to 0, roughly speaking, as 1 over m to the power R. Also, we can characterize the function spaces LUP and the Zygmund spaces by means of the error of best approximation. First of all, by means of the moduli of smoothness, and then by means of the error of best approximation, which is useful when you study functional equations, for instance. In our case, was useful in this case, in this sense. And to conclude this section, just a few words about this embedding theorem, because here you can see we have the condition under which a function belonging to LUP with p less than infinity is continuous on the whole interval -1, 1, which means that we can interpolate this function. So we use this result in this way. Okay. Now let's talk about Lagrange interpolation. We want to consider some concrete approximation process. We said something about the error best approximation, and we would like to construct some concrete approximation process, and we consider the Lagrange interpolation based at the zeros of a Pollacek type. And this is the standard definition of Lagrange interpolation, but the problem here is that the Lebesgue constant associated, for instance, in the space related to the weight square root W, has not an optimal order, which I mean that it grows like m to some power. Tau is not important, the value of tau, but it's not like, do not behave like log m. This is the problem. So this is not really surprising, because a similar phenomenon course also for other exponential weights. This is always true with exponential weights. Also for classical weights, Laguerre weights, Hermite weights, Freud zeros, we have similar phenomenon. And how we solve this problem? We slightly modify this operator. And I will say immediately how. First of all, we consider not only the zeros of PM, but also two additional points, plus and minus AM, the two Mascart-Rachmaninoff numbers. And then we fix some theta between 0 and 1, just to say that we do not consider all the zeros, all these m plus 2 zeros, but only a portion which drops the terms close to plus and minus 1. Then we define the fundamental Lagrange polynomial, as usual, with these two additional nodes. And our Lagrange operator has this form. Notice that this is a polynomial of degree m plus 1. It's based on m plus 2 nodes, so as degree m plus 1. But in the definition here, we do not have all the nodes, but only the terms related to a portion of the nodes. This means that this polynomial interpolates the function only at the zeros which lie inside this interval, this subinterval, and vanish at the other zero. Okay, so this is not really what we usually think about when we talk about Lagrange interpolation. So it interpolates, but only in some subinterval. And also, this is not a projector in the usual space of polynomial, of course, because we have this. So a polynomial, this is a polynomial of degree m plus 1, but if we apply this operator to a polynomial of degree m plus 1, in general, we have a different polynomial. But if we consider this subspace of polynomials, the polynomials of degree m plus 1, which vanish at the nodes that we dropped, then it's trivial. These polynomials belong to this space, and this operator is a projector into this space. This is trivial, of course. The less trivial thing is that the union of these polynomials is also dense in weighted LP spaces. And we proved that there is a connection between the error of best approximation by means of this polynomial and the error of best approximation by means of the usual polynomial. They behave more or less the same. And in this space of polynomial, we can prove under suitable assumption the two Marcinkiewicz inequalities. So the weighted LP norm of a polynomial is equivalent to this discrete norm of the polynomial. So what is the advantage? I will show you that with this kind of polynomial, of course, we will have optimal result. But so this is the advantage from the theoretical point of view. From the numerical point of view, I also want to point out that a function f belonging to the space I have introduced grows exponentially, can grow exponentially at the endpoints. So it doesn't make too much sense to interpolate the function where it has big values. So this is also one practical reason why we choose some subinterval and we interpolate in some subinterval. Then about the convergence, first of all, from the Marcinkiewicz, the second Marcinkiewicz inequality is equivalent to this, to the bound, in some sense, the boundedness of the operator under proper necessary and sufficient condition, which involves, I want to point out that this condition involves the algebraic part of the weights. So this is the reason why we have chosen these weights we have defined the weights in that way. I also want to point out that you can also drop the algebraic part and obtaining the convergence, for instance, for smaller values of P. But here we were interested in obtaining the convergence for P between 1 and infinity. And for P equal infinity, we have, of course, the log M. I just want to show you some more explicit estimates. For instance, for function belonging to some sublet space of index R, this process under the previous assumption, this process converges like the best approximation. So like 1 over m to the power r for P less than infinity, strictly between 1 and infinity, while for P equal infinity, we have the extra factor log m. But of course, we still have convergence. And similar results also for Zygmund spaces. And moreover, we can show that the associated operator is uniformly bounded in Sobolev and Zygmund spaces with the same assumptions. Now, just a few words to say the reason why we truncate it from another point of view. We start from these inequalities. These are, I think, well known in some sense. The weighted norm of a polynomials is bounded by the weighted norm of the polynomial inside the Mascar subinterval. And outside this norm decays exponentially. From these inequalities, we can deduce that also the norm of a function, weighted norm of a function, is bounded by the weighted norm of a function inside some subinterval of -1, 1, plus this term, the error of best approximation, which decays faster. So roughly speaking, the norm of the function also, the essential part of this norm also is in the subinterval. It's not only all -1, 1. And this is due to the presence of a weight which decays very fast, of course. Okay. I will be very fast here. I will not show all the details, but I just want to mention that recently we have considered the Hermite and Hermite-Fourier interpolation associated with Pollacek type weights. And the results, the results about Lagrange interpolation can be applied also to study this kind of process. And as for Lagrange interpolation, we define Hermite interpolation of the first order, I mean. We define the Hermite interpolation in the standard way, except from the fact that here we consider n+2 nodes, again, these two additional nodes, and we drop some terms in the sum in the same way. In this way, we obtain something which is similar to Hermite interpolation. So we have similar interpolation properties, but also which vanish at some 0 that we dropped in the sum. It's also well known that we can split as usual. Let's say, as usual, we can split the Hermite polynomial into two parts: the Hermite-Fourier polynomial and this other part. The Hermite-Fourier polynomial is a polynomial that interpolates the function at some nodes and whose derivative is 0 at the same nodes. In this case, it interpolates the function at the zeros which lie inside the subinterval. Again, this operator is not a projector in the standard space of polynomial. We have to define proper subspaces of polynomial. I also want to mention that we can see this process as the standard Hermite interpolation with the two additional nodes apply to a finite portion of the function. And using also our results about Lagrange interpolation, we can prove the convergence of this process in weighted LP space and in the weighted space of continuous function. I will, I have the slides, but I will skip them. I only want to show you one example. For instance, in sub-Lev space, we obtain for Hermite interpolation in weighted uniform metric the order of the best approximation multiplied by log m as for Lagrange interpolation. So this process converges slowly in some sense, but we are only in W1, so function having also only one derivative. And okay, if I have some few minutes, I think. Okay. Okay, so I just want to give you some ideas of different, in some sense, application of these results, because this is not really a direct application, but the topics are strictly connected, actually. And if you think about, for instance, the classical Erdogan-Turan results about convergence of Gaussian quadrature sums related to the convergence of Lagrange interpolation, these topics are very closely connected. And so I will show you some examples concerning integration. But first of all, as promised, I want to say something about the computation of these zeros. The three terms relation is not known in explicit form, so we have to compute the coefficients alpha k and beta k. We used the Chebyshev method of moments, standard Chebyshev method of moments, and to overcome the numerical instability of this method, we used variable precision arithmetic in Mathematica, using a package that you can find also in Milovanovic web page. And then we worked in double arithmetic. So we worked in extended precision only to compute this coefficient, and then the other things are standard in some sense. And this is one motivation why to study this kind of problem, for instance. Just a simple example, we have an integral between minus 1, 1 of a function which is very smooth, okay? But it decays exponentially, not really so fast. But we can see also with this kind of function that the Gauss-Legendre rule is not suitable in this case. Why? For many reasons. I think the main are that if you look at from a very analytic point of view, here we have some derivatives. The norms of the derivatives grow very fast. So this is C infinity. So this function is C infinity, but the norms of the derivatives are I, because we have some factor here when we compute the derivatives. This is the first thing. The most simple thing is that here we have an integrand which decays fast, close to plus and minus 1. We use the Legendre rule, so we compute the function where it is 0. So this does not make any sense. So the best thing is to compute the function where it has some significant values. And this is why the rule that uses this part as a weight function behaves much better. We obtain the double arithmetic precision with a few points. And also for Gaussian rule, we can consider truncated rules. And this allows to use less points, less evaluation of the function. So here we have the degree of the polynomial that we used for the zeros, but the function evaluation are smaller. In this case, the convergence is not so fast because we have a not very smooth function, and the order of convergence is 1 over m to the power 5 over 2. And just an example to give you the idea for in the case of Fredholm integral equation of second kind. Here we have a function, a right-hand side, which grows exponentially at the endpoints. And so also the solution of this function, this is not known, the solution of this equation, but the solution of this equation will behave, will have a similar behavior. The class of the function f is determined by the class of the kernel function and the right-hand side. We are sure that there is a one solution, one and only one solution, because this norm is bounded by 1. And you can see that in this case, I only choose 2 points, but it is the same in the only interval. With very few points, we obtain the double arithmetic precision. So here we have a linear system of order 8 in order to get the machine precision. And also, of course, the metrics associated are well conditioned. Okay, I will stop here. Thank you. Thank you for your attention.
Are there any questions?
Yeah. I'm sorry, I didn't. The Sobolev space? In which sense? Mm. Linear is a linear operator, yes. Linear, you mean with linear, you mean a linear operator? Yes, it's a linear operator. Yes, yes, yes. Yes, we can prove that these operators are uniformly bounded in LP spaces for P strictly between 1 and infinity. Not in general, but in proper spaces of functions. Yes. We can see this is yes, everything can be done, but it requires time, of course. Yeah. Yeah. Okay. Okay. Thank you.
I think we need to stop our discussion because public lecture. So
okay. Thank you.